And we'll also define the third law of thermodynamics. Okay. So what was the first law of thermo, just for fun? The first law of thermo was conservation of energy. I can't create or destroy energy. There's some absolute amount of energy in the universe. We were like, oh, think about conservation of mass. You can't create and destroy. Same. Conservation of energy. What was the second law of thermo? Okay, the direction of entropy in the universe is always positive, okay? So the direction of things is always towards max entropy, okay? So that was the second law. We had a zeroth law, if anyone remembers. Zeroth law was actually the fourth law they wrote down. They came up with it after the fact and put it at the beginning. It was thermal equilibrium. If A is at a given temperature and it's at the same temperature as B, and C is at a certain temperature and it's at the same temperature as B, A and C are also in thermal equilibrium, okay? And we let temperature be a metric. It is sort of a way for us to think about average kinetic energy of our systems. So now we're into law number 3. Okay. What is today? 11/4/19. Okay. So the absolute entropy of a system can be determined with a heat capacity measurement. A system can be determined with heat capacity measurements. Okay, so something like differential scanning calorimetry. And the way we define absolute entropy, so we can write entropy, capital S is our notation for entropy. If we put ABS as sort of a subscript here, this is the change in entropy for entropy at temperature equal to T2, some temperature of interest, whatever it might be, sort of final temp, minus the entropy when T is 0 Kelvin. Okay. So we put everything relative to 0 Kelvin. This term here is entropy at absolute 0. And we let this be equal to 0. Okay? So what the third law of thermo states is that entropy is 0 at absolute 0. Entropy at absolute 0 is 0 per the third law of thermo. And the way we think of this is that at absolute 0, everything stops moving. Everything is a solid, and everything is sort of frozen's a poor word, but it's exactly in one. It's frozen. It's absolute 0. Everything stops moving and exists in exactly one configuration. And since entropy is equal to Boltzmann times the natural log of multiplicity, then if we let this be, if at absolute 0 we have exactly one way that everything has to be, once everything stops moving, becomes a solid and nothing changes, and it's only one way for that to happen, this is equal to 0. Natural log of 1 is 0. So when we talk about absolute entropy of a system, we think about it as just the entropy at that temperature, and we already took it relative to temperature 0. Okay. So our thermodynamic or classical definition of entropy, let's write classical, was given by change in entropy would be reversible heat transfer over the temperature that we're at. And something else we can say from before is that our constant pressure heat capacity, this was equal to dH dt, change in enthalpy with respect to temp, or change in constant pressure heat flow with respect to temp. Heat capacity was how much heat do I have to put in to get temperature to change 1 degree, okay? So how much heat do I have to put in to change 1 degree? This relationship is valid because delta H was equal to constant pressure heat flow by definition. So then I can rewrite this as change in heat is equal to constant pressure heat capacity, change in temp, and plug this in to Q reversible in my entropy equation. Okay. So the entropy equation in its differential form is ds is equal to dQ reversible over T. I'm going to plug this piece into the top. So this is equal to Cp dt over T. So then if I actually want to integrate this, I'll get change in entropy is equal to the integral from 0 to T2 of heat capacity over temperature dt. I can pull heat capacity out into the front. This will be equal to 0, T2, 1 over T dt. The integral of 1 over something is the natural log. So this is Cp, the natural log of temp. As we go from 0 temp to some temp of interest, by properties of natural logs, I can write this as natural log of T2 minus the natural log of 0. But I'm just going to ignore this piece. Absolute entropy at a given temp, T2, is just equal to Cp, the natural log of T2. This was change from 0 Kelvin. In a more general form, if you were interested in actually getting a change in entropy if you were going between two temperatures, so then sort of a general form. I think people were maybe upset before, this would be between T2 and T1, you weren't going between 0, that I didn't go through this, and then we had one team present this problem on review day and did this integral for you correctly, and then I said, oh, make sure you know how to do that. And I didn't put it on exam 2, but it's fair game for exam 3, so make sure you understand how this worked. But those people did it perfectly, so. Okay. So if I have temp on this axis, so we're used to seeing a calorimetry for, say, the unfolding of protein. When we had heat capacity over here and we had temp over here, it looked like, oh, nothing's happening, and then it looked something like this, right? Here we were just raising kinetic energy or temperature for our protein unfolding DSC experiment. And then here, changes in potential energy were happening as we unfolded something. Okay. So now if we plot molar heat capacity, joules per mole Kelvin. Molar heat capacity, you might see it with the superscript on it. It just means I'm only interested in 1 mole. Anytime you see that, put it in 1 mole. I think I saw a question on Piazza that was like, oh, hey, should I divide by 2 if I've made 2 moles and you've asked for molar? Yep, that is how you should think of that. So this is joules per mole Kelvin. And if this were 0 T, which we can't really get, but we'll get maybe some curve that looks like this. And if you integrate the area under this curve, underneath the curve of Cp over T, okay, that's that. From T1 to T2, this area is equal to delta S. And so again, we can kind of, between those two temps, this is the curve for molar heat capacity over temperature. We can't really actually do a DSC experiment down to 0 Kelvin, obviously, but we just extrapolate our calorimetry data to get our absolute S as integrating from 0 to T. So you could go ahead, run an experiment, get a CP value, plot it as heat capacity over temp, integrate under that curve, and get yourself an entropy change. You will, of course, always be given an entropy change in this class. I won't ever ask you to integrate area under this curve because we have computer software to do that for us forevermore. The calorimeter will do it for you. But it's important to understand where that number comes from, and that if you're given some molar entropy, how did we get it? Okay, it came from a difference between absolute 0, and it was measured using calorimetry at some point. Okay. Yes?
So, on the document which we had with change in potential energy as we unfold, I understand that. But can we also equate potential energy to heat capacity at this point? Like CP?
So yes, so here CP is changing. Basically, it gets harder and harder to raise the temperature by 1 degree because I have all this potential energy. Here I'm just raising it. Temperature is going up because all I'm doing is raising T 1 degree, so CP is really low. Over here, it gets harder to raise 1 degree. I have to put in more and more heat because I'm actually unfolding something and disrupting some sort of potential energy interactions. This is a plot of CP over T. And so molar heat capacity is changing as temperature goes up. This was specifically for unfolding a protein. This is the general shape for, maybe it's just elemental oxygen, maybe it's just glucose. I don't know what it is. Yeah, these don't like directly one-to-one compare. Yes, this shape over here is what our DSC curve looks like. Where am I? For unfolding a protein. That's the shape you would expect to see. Or maybe pulling apart 2 strands of DNA like on the exam.